Hey everybody, Matt from 90th percentile.ca here. For access to more study notes, practice questions, mock exams, and end of chapter question videos, visit 90th percentile.ca and sign up for your free trial today. Link below in the description. This learning module is organizing, visualizing, and describing data. Quick overview on this module. It's very, in my opinion, very fluffy at the beginning. The first, call it 50% of the reading in the book is talking about different types of data, gives you some different definitions and characteristics for like continuous data versus discrete data. And then also goes into different types of charts, like line charts, bar charts, all of that. In my opinion, very unlikely to show up on exam day. I don't see a case where they show you a graph and then ask you to tell you if it's a line chart or bar chart. What I would recommend for the first, call it 50% of this module, is just to read over your notes, make sure you're familiar with some of the key definitions for the different types of data, just in case by chance it shows up on exam day, it's not completely foreign to you. Um, but throughout the end of chapter questions, we're largely going to skip questions that are related to this type of stuff, mainly because, like I said, I really don't believe it's going to be a reflection of what's on exam day. We'll go over some questions related to these topics here, but for the most part, we're going to spend all of the time in the second half of the learning module, which is really what's important on exam day. And here's where you're actually going to have to do some calculations for some different means or averages. So you have the arithmetic mean, geometric mean, and harmonic mean. We're going to go over these in the questions. We'll show you the formulas and explain what each is used for. There's also some measures of dispersion, with the main ones being variance and standard deviation. And there's also some small tweaks that we're going to make on the standard deviation formula, which we'll see. Next, we also have some skewness and kurtosis definitions, which are really just used to describe the shape of a distribution. So like you have your normal distribution here, whether it's skewed or has some kurtosis will change the shape of this graph and also has some implications for the data that we're looking at. And then finally, correlation. Learning module touches on it very briefly towards the end, but we need to be familiar with what this is and how to calculate it. So with that, let's get into the questions. Question number 4, a fixed income analyst uses a proprietary model to estimate bankruptcy probabilities for a group of firms. The model generates probabilities that can take any value between 0 and 1 or 100%. The resulting set of estimated probabilities would most likely be characterized as ordinal data, discrete data, or continuous data. So there's a bunch of questions in this chapter that are pretty much the same thing, and they're just a matter of differentiating between these different types of data. Not really important for the exam, in my opinion. Pretty unlikely to ask you something like this, but we'll go over one question. We don't want to be redundant and go over like 10 questions of the same thing, so we'll do one, and then it's just a matter of you understanding the definitions and being able to differentiate between the different data types. So A is ordinal, B discrete, and C is continuous. So ordinal data is a set of numerical data that can be ordered and ranked in a logical manner. So an example of this would be ranking different hedge funds, so like hedge fund 1, hedge fund 2, hedge fund 3, based on their returns that they have achieved over the year. Discrete data is just, it's only related to integers, so whole numbers 1, 2, 3, 4, and continuous data can take infinite values. It has a possibility to be any one of the values in between a certain range, or it could be go to infinity or whatever. But in this example right here, so we're worried about probabilities. So the model generates probabilities that can take any value between 0 and 1. So from 0 to 1, or 100%. One of the things with continuous data, and this is a pretty important stats concept as well, you'll see when we get into the probabilities module, it's more relevant there. But if you were to draw out, all the values that this model could take, all the probabilities that it could take out, or it could be essentially infinite values in between 0 and 100%. And what we mean by that is that it could be 99%, but 99.92, 4, 1, 5, 6, 7, and the decimals could just go on forever. So one of the foundational topics in stats is that the probability, so let's say this variable can take any value between 0 and 100%. The probability that it's exactly equal to one number, so let's say probability that it's equal to 99.0% is 0. Because once again, it's kind of one of those weird things where there's assumed to be infinite values in here. So the probability of being exactly equal to one number out of a set of infinite numbers is 0. But you can kind of group, where the probabilities come in is that you can group the probability that it's between like 95 and 97, and you can determine a probability for that because it's a range of values. Whereas here we're worried about one value, one decimal, when decimals can go on forever. But anyway, answer here is going to be continuous data, which is the case with probabilities at it's just always a case with probabilities. It can take infinite values in between a certain range. Questions 6 and 7 are combined here, where we have an equity analyst gathering total returns for 3 country equity indexes over the past 4 years. We have the data here in the table. So we have years going along the rows, and then the different indexes across columns. So for 6, each individual column of data in the table can be best described as, so if we're looking at a column, so if we're taking index A, and we're looking at this whole column, we're comparing the data over years, which is time series data. So that's comparing a certain data set over a period of time. Whereas if we're looking at the rows, let's just take this one. If we're looking at this row, we have a certain period of time and we're comparing different data points or different indexes in this example. So this is an example of cross-sectional data where it's a snapshot in time and we're comparing information across different data sets. 12 and 13 are also combined here. So we have a fixed income portfolio manager creating a contingency table of the number of bonds held in a portfolio by sector and bond rating. The contingency table is presented here. So we have sectors down here and we have their bond rating across the columns. The marginal frequency of energy sector bonds is closest to. So the marginal frequency is the sum of the row of the energy sector. So all we're trying to do, the marginal frequency is just asking how many energy bonds are there in this table. So it's going to be the 100 plus the 85 plus the 30, which you get to 215. So the marginal frequency is always just either summing rows or columns. If they were asking the marginal frequency of A-rated bonds, it would just be the sum of this column here. Then the relative frequency of AA rated energy bonds based on the total count is closest to which one of these. So we're worried about the relative frequency, so the percentage of the total that AA rated energy bonds represent. So come to the table, we have energy here and AA here, which are 85. So we have 85 AA rated energy bonds versus the total count, which would just be the sum of everything here, sum of every single value in this table. Not going to add them one by one, but if you were to do it, you would get 806. And 85 divided by 806 is 10.5%. So your answer is A. 21 and 22 are also combined. And we have a histogram here showing a distribution of the S&P 500 index annual returns for a 50-year period. That's important. So, we have a chart here. We have the frequency, which is how many times a return in this range occurred. So if you're looking at this, we have negative 37% to negative 32%. This happened once over a 50-year period. And it's the same across all these, the same logic across all the observations here. Number 21, the bin containing the median return is which one of these? So the median for a even number of observations will be actually the average between the most two middle observations. So like really quick, I know this is really basic. I know that I promise this is the last kind of unimportant question we'll go over in these end of chapter questions. After this, we start to get into what actually matters from this learning module. But anyway, let's say we have 3 observations. The median is in the middle, so that would be the second observation versus 1. We have 3 and 4. the middle is technically these two combined, so you would take the average of these two. So in this case, we have a 50-year period, which is an even number of observations. So the median would occur in between the 25th and the 26th data points. So here we can do some really quick math to figure out where the 25th and 26th observations lie. So if we're going to add these up from left to right, so we have 1, 2, 3, 4. 4 plus 4 is 8, plus 3, 11, plus 2, 13, plus 7 is 20, and then 8 to 13, this brings us to 24. And then as we come here, we have 6 observations in the 13 to 18%, and this is where the 25th and 26th observations lie. So the bin containing the median return is C, 13 to 18. And then 22, based on this histogram, the distribution is best described as being unimodal, bimodal, trimodal. So all this means uni, bi, tri, so 1, 2, 3. Unimodal is a data set having one mode, and a mode is the value that occurs the most. You can see here that we have in 3 to 8, and in 18 to 23, and 28 to 33. All of these are occurring 7 times. So it's going to be trimodal because it has 3 modes. So question 24, this is where we actually get into the important stuff from this module. And from here on out, we're talking about how to calculate different types of returns, and worried about shapes of distribution and the implications of those different shapes. So here, question 24, at the beginning of year X, an investor allocated his retirement savings in the asset classes shown in the following exhibit and earn a return for year X as also shown. So we have the returns here, and we have the asset allocation across these different asset classes. So we have like large cap, small cap, etc. So the portfolio return for year X is closest to, and for this, all we got to do is take the weighted average of the asset allocation and the returns. So going from top to bottom here, we have 20% in large cap US equities times 8% return. And then we got to add the 40% weighting of the small cap times a 12% return plus 25% of emerging markets times -3. And then we can also add the 15% in the high yield bonds times 4. So you run this calc out and you get 6.3, so C. So here we have a following exhibit, and we have the returns for the fund across a bunch of years, and it's asking us what the geometric mean return for the fund is. So before we do that, I just wanted to use this as a quick learning lesson in terms of the difference between the normal mean, which is just like a simple average, and the geometric mean. So the geometric mean is always used when calculating portfolio returns over time, and to show you why, we're going to come up to this diagram over here. So let's say we have $100 in our portfolio right now. At the end of one year, it turns into 120, and at the end of the next year, it turns into 75. So year over year, from year one, we get a 20% positive return, and then year over year, from year 1 to year 2, it's a negative 37.5% return. So if we were just to take the simple average of the return, so the 20% minus the 37.5% divided by 2, we get a stated return, annual return of negative 8.75%. So let's just keep that in mind for now. And then we're going to come here and calculate the geometric mean, which accounts for the compounding. So here, same kind of concept. You have the $100, 120, 75. So you take the returns, 1 plus 20%, multiply it by 1 minus 37.5%, put it to the power of 1 over 2, which is the same as taking the square root, and subtract that by 1 to calculate the geometric mean. There we get a return of 13.4, negative 13.4%. So if you take both of these and you come over here to the left-hand side, you can see that in this first example, I'm using this simple mean return, so the negative 8.75. And if we take our $100 and multiply that by a negative 8.75% return for 2 years, so to the power of 2, we get a value of $83.26, which is much greater than the 75 that we're actually left with. And the reason for that is that the simple mean doesn't account for the compounding that occurred from year 0 to year 1. So we actually went not from $100, but 120. So like this simple mean is assuming that this 37.5% was based off of this 100, not the 120 that it actually was at the end of year 1. Versus if we do the same thing, take the geometric mean $100 times 1 minus 13.4%, which is the geometric mean, and compound that twice for 2 years, we get the value of 75, which is actually what we're left with. So, just thought I would highlight this. It's pretty important. Some people might not spend too much time thinking about this, but it is important to note, especially when dealing with portfolio returns, that the geometric mean always makes the most sense because it accounts for the size of the portfolio and the associated returns year over year. So now back to the question. The following exhibit shows the annual returns for Fund Y. We have the returns and 5 years of data. One other thing really quickly that I thought I should mention here, we're going to use 5 periods in the calculation because we're showing the yearly returns. In the example I showed with the 100 and what was it, 120 and 75, this was time is 0, time is 1. So this is technically 1 period. And then from here to here, T1 to T2 is 2 periods total, even though there's 3 data points. So be careful with how they present the data to you. Here we're giving 5 years of return, so there's actually 5 of these periods here. So we're going to just get rid of this. And now we're going to have the geometric mean return for Fund Y, which is 1 plus 19.5% times 1 minus 1.9% times 1 plus 19.7%. And I'm just going to continue this on the next line, times 1 plus 35% times 1 plus 5.7%. And then we're going to take this whole thing, we're going to run these calcs out, and then we're going to put everything to the power of 1 over 5, because there's 5 periods, and subtract 1. And our answer ends up being 14.9%, which is A. Portfolio manager invests $5,000 annually in a security for 4 years at the prices shown in the following exhibit. The average price is best represented as the harmonic mean, geometric mean, or arithmetic average. So what we're trying to do is figure out pretty much the weighted average cost of the shares that this portfolio manager has. We're putting in 5,000 annually, and the price is different in each year. So we're actually going to get a different amount of shares in each of these purchases. So like we're obviously going to get more when the price is 62 versus when it's 90. Looking back at our answers, right away you can cross out geometric means. Geometric mean is useful for compounding, and it's pretty much just for portfolio returns. It's not relevant here. The arithmetic average would simply just take the sum of these and divide it by 4, which isn't useful either because, like I said, we're getting a different amount of shares in each year. So it wouldn't account for the different prices. So we can actually cross that one out as well. The answer is going to be A, and we can either just leave it as is, but I can show you the work in terms of how this is calculated. In the textbook, it uses the harmonic mean formula, which is 4, so the number of observations divided by the reciprocal of these prices. So 1 plus 62, 1 plus 1 over 76, plus 1 over 84, plus 1 over 90. Sum up everything in the brackets, take 4 and divide that by the answer, or by the sum here, and you get the 76.48. This way it works. It might not be as clear intuitively. So the way I thought of this question when I first looked at it is to do it like this. So I would have year 1, year 2, year 3, year 4. We're putting 5,000 in each year. And in year 1, the price is 62. So we're going to divide each year to figure out how many shares we're getting. So Year 2, it's $76. Year 3, 84. Year 4, 90. So here we're going to get 5,000 divided by 62, 80.6 shares. Here we're going to get 65.8. Here we're going to get 59.5. And then here we're going to get 55.6. So these are the number of shares that we purchased in each year. If you sum all this up, you have 261.5 shares. And we invested 20,000, so 5,000 over 4 years. So $20,000 divided by 261 shares gets you an average price of 76.48, which is the answer in A, which we crossed out just by reading or understanding the differences between the types of averages, and we calculated here and here. So we're all good. When analyzing investment returns, which of the following statements is correct? The geometric mean will exceed the arithmetic mean for a series with non-zero variance. This is incorrect. The relationship between the three mean calculations that we talked about is this. So we have harmonic, we have geometric, and we have the arithmetic. So the harmonic is always less than or equal to the geometric mean, which is always less than or equal to the arithmetic mean. And the only case when these will be different, so when they're not equal, is when there is some sort of variance in the values. Let's say we have values of 80, 80, 80, 81, 82. If we calculate the harmonic mean versus geometric versus arithmetic, harmonic would be the lowest, geometric in the middle, arithmetic the highest. So whenever there's any sort of variance between the values, they won't be equal. They will always follow less than, middle, greatest. If there is no variance in the value, so if we're doing 80, 80, 80, 80, we want to calculate the three averages, all these are going to be the same. That's just something to note going forward. But anyway, A's out. B, the geometric mean measures an investment's compound rate of growth over multiple periods. Yes, we talked about this multiple times, so this is the answer. You can read C anyway, though. The arithmetic mean measures an investment's terminal value over multiple periods. Like this, just all over the place. The terminal value is related to calculating the present value of stocks at some point in time in perpetuity. We'll get into that later. This is just completely wrong. So answer is B. A fund had the following experience over the past 10 years. We have their years and their returns. The geometric mean return over the 10 years is closest to which of these? All the values are really close, so we got to make sure we're really paying attention when we're inputting values in our calculator. But geometric mean return is going to be 1 plus R for all of the returns, multiply them together. It's Rn. And then put this to the root of 10, which is the number of observations, and subtract 1. That's the geometric mean return formula. This would really be n, but here I'm just using 10 because that's the number of periods in the example. So we can do it really quickly. Just add 1 to all of these. 1.06, 1.5, 0.98. This is 1. Sorry, it's getting a bit crunched up there. 1.045, 1.035, 1.025, 1.055, and 1.04. Multiply all of these, and we get 1.3402. And it goes on for a bit, but that's fine. And then we put this to the power of 1 over 10, which is the same as the root of 10. Subtract 1, and our answer is 2.9717%, which is B. 30, same thing, just got to calculate the harmonic mean this time. So one thing quickly to note about the harmonic mean, we're dealing with returns now. So in the previous question where we were dealing with the average prices, what do we have? We had 4 observations. It was 1 over 62 for the stock prices, and we kind of went along for the other ones. And it was 4 divided by this. Here, when we're dealing with returns, there's an additional component to the formula. So instead of just having, in the case of the stock price is 1 over 62, here it's going to be 1 over 1 plus the percentage, 4.5%. And then we go all the way down to 1 over 1 plus 4%, which is this value here. I'm not going to do all of them just for the sake of time, but you would take the reciprocal of 1 over, or not, it's 1 over 1 plus the percentage. Sum all of those up, and then when we take the harmonic mean, we do 10 number of observations divided by this whole value in the brackets, and then subtract 1. So when we're dealing with returns, don't forget to add the 1 before the return, and also subtract 1 after the fact, where we did not do that here when we were dealing with prices. But anyway, you run this calc out. I'm not going to do every single one just for the sake of time, and you end up getting a harmonic mean return of 2.94%, which is A. 31, still dealing with the same data set, but now we're asked to calculate the standard deviation. So two ways you could do this. One is to use the traditional standard deviation formula, which is standard deviation is equal to the sum, let's do that right, from I equals 1 to n of xi minus x bar, which is the average, squared over n minus 1, which is just, analyzing the square differences from the mean. So to actually do this by hand would take a lot of time, and I don't recommend it. There'd be a couple steps. So one would be to calculate the difference between the return, so like 4.5%, and the average, which you also don't. We don't have the arithmetic average, but you would just take that. You have to calculate it, figure it out from this, and then across all these observations, the value, so 4.5% minus the average, 6% minus the average, etc. Second step would be to square it. So you would take all of these values, square them. Third step, you'd sum them. And then you would have this part of the equation up here. Fourth step, divide it by n minus 1, which is 10 minus 1 in our case, so 9. And then fifth step is to take the square root of everything. So it seems like a lot of work. Once again, want to help you guys really take advantage of your calculators. So don't forget to check out the links that I have on my website for all the calculator help. But here I'll show you a really quick example. I urge you to follow along, where we could actually enter in all these data points in our calculator, and the calculator will give us a bunch of different stats related to it. So we could actually come to our calculator, press second, and data, and now you'll see this menu comes up. I have x01, which is just like the first value of x, is equal to what? So I would go down the list here. For x01, I would press 0.045 and then enter. And then you can just press up on the calculator and just go throughout all the values. So x03, x04, all the way to x10. And then you press, when you have all the data in, you press second plus stat. And you'll get the lin come up first, which is just a different value. But if you toggle up and down, you can see that we have, like if I press down, the first thing I see is n is 10, x bar is 3%, and sx, which is our standard deviation, is 0.0253, which is our answer in B. So just a really quicker way. This method up here, you can do it. It just takes a long time, and there's a lot of room for error. So I recommend, once again, use your calculator, use your calculator, use your calculator. Last question with this data set. Here we want to get the target semi-deviation of returns over the 10 years if the target is 2%. So semi-deviation, only difference, it's the same thing as the standard deviation formula we just looked at. sum I equals 1 to n xi. But here, where we normally have x bar, this is actually going to be the target, so the 2%, and then n minus 1. Everything else is the same, but in this case, we only care and we only incorporate the amounts that are actually less than the 2%. So it would be this, 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 and that's it. So here, unfortunately, there's not a way to do this on the calculator with the data and the stats functionality, or at least not that I know of. So what we would actually do is the long way here. So it would be, what we have to do is first calculate the values in here, and sorry, this is squared. If you notice that, good. So first, we're going to calculate xi minus x bar, or the target, so 1.5% minus 2%. And the next one is negative 2% minus 2%. The last one is 0% minus 2%. And then we would take all of these, square it, and we end up getting, here, let's move this down. So this is 1, this is 2, this is 3. 1 is 0.0000025. 2, 0.0016. 3, 0.0004. Sum all these together, and we get 0.002025, which is the numerator of this fraction right here, because we took the difference and then we squared it and then we summed them up. So this value here is the whole numerator. So from here we got to take the square root, or first go 10 minus 1, and then take the square root. And our answer, once we do that, is around 1.5%, which is B. Following exhibit shows the annual MSCI World Index total returns for a 10-year period. So year 1, 2, 3, 4, 5, data's kind of all over the place, not organized in order, but that's fine. Well, it's organized in chronological order, but not in the order of returns. But anyway, you're going to see why that's a problem in a second, because we are asked to calculate the fourth quintile return for the index. So a quintile divides data into fifths. So quin is fifths, just like percentile is hundredths. So the fourth quintile would be 4 over 5, or 80%. So the fourth quintile is where 80% of the returns are below that. Just like if you're 90th percentile, 90% of whatever you're analyzing is below where you are. So in order to calculate the position of a percentile in an array or a quintile in an array, we can use this formula. Ly representing the position or the observation where this 80th percentile or fourth quintile occurs. It's the same thing. So Ly is a position, and we go n plus 1, n being the sample size is 10, and then y is the percentile or quintile. In this case, it's 80th percentile times 80 over 100. So we find out that Ly to 11 times 80 over 100, which is 8.8. So this is the position if the data was ordered from least to greatest. This is the position where that fourth quintile return occurs. So once again, don't think you would see this on the exam. It would probably be ordered for you, but we can do some quick sorting here to kind of figure out where the eighth return is. So the low. So once again, ordering from least to greatest. The least is this. So this is 1. 2. That's -5. 3, 4, 5, 6. This is actually less than that, but it doesn't matter. 6, 7, and then we're left with 3. And the eighth, from least to greatest, would be 20.65, and the ninth is the 27.37. So the fourth quintile return is actually going to fall somewhere in between this 20.65, which is the eighth value, and the 27.37, which is the ninth value. So when the position that you find isn't a whole number, so if this was 8.0, the answer would be 20.65. Let me see, that's an answer here actually, so we can cross that off. But given that it's 8.8, what we do and what the curriculum does is it essentially assumes that there's a linear relationship between this 20.65 and the 27.37. So for, if we were to draw this 20.65, 27.37, and we're worried about the 8.8th position. So we're gonna have to get 80% of the way here on a linear curve. So the way you would do that is you would take the eighth position, which is 20.65, plus 80% of the difference between the two, 27.37 minus 20.65, and you run that out, and you get a value of 26.03 right here. Looking at answer C right now, actually, you can see 27.37 was here as well. So even if we just calculated the position as 8.8 and we looked and we saw that, okay, one of them is 20.65, one of them is 27.37, you can kind of know just by looking at the answers that 8.8 lies in between them. So like A is an exact value in this table, C is an exact value in this table, so you could probably just eliminate them right away. Anyway, I thought I would show you the work in case you wanted it. 36, same data set, but now we just gotta calculate the mean absolute deviation for year 6 to 10. Mean absolute deviation, a similar concept to standard deviation, but the formula is actually sum from I equals 1 to n of the absolute value of your x value and the mean over n. There's no squared or anything here. So the absolute part of this equation is just referencing these absolute bars here, which of course will ignore the signs of the positive and the negative values, just the absolute value between the two. So we can do it really quickly. First thing we have to do is calculate x bar, which is going to be the average, so 30.79 plus 12.34 plus minus 5.02 plus 16.54 plus 27.37. Sum all these up, divide it by 5 because we're just dealing year 6 to 10. And we get a mean of 16.40. So now coming over here, we do this, minus all of these minus 16.40, minus 16.40. And absolute value across all of them. So here, let's go in order. So this will be 1, this will be 5. We'll bring it down here. So when you run these absolute value, the difference in the absolute value calc, for 1 you get 1439. Here 4.06, 3, 21.42, and this is the only place that we have a negative, so this is where the absolute brackets actually come into play. Here is 0.14, here is 10.97. Sum all of these up, get 50.98 divided by 5, and our mean absolute deviation is 10.20%, which is A. The average return for portfolio A over the past 12 months is 3% with a standard deviation of 4%. The average return for portfolio B over the same period is also 3%, but with a standard deviation of 6%. The geometric mean return of portfolio A is 2.85%. The geometric mean return of portfolio B is less than, equal to, greater than. It's going to be less than. We said earlier the geometric mean is always less than or equal to the arithmetic mean, so it can't be greater than. It could be equal to, but here we have the variance is greater than in portfolio B than in portfolio A because it's 6% versus the 4%, which causes a greater difference in the mean return calculations. The greater the variance, the greater the difference between the geometric mean and the arithmetic mean. If you were curious, the geometric mean is always equal to arithmetic mean less 1/2 of the variance of the returns. It's not equal to, it's approximately equal to. So you can see here that with a greater variance, it's going to be even less than the arithmetic mean because we're subtracting this. So answer is A. The mean monthly return and the standard deviation for 3 industry sectors are shown in the following exhibit. We have the mean returns here, standard deviation of returns here for a couple different sectors. Based on the coefficient of variation, the riskiest sector is. So what is the coefficient of variation? So it's a bit different than like standard deviation, variance, all that. And what it is it's a simple ratio of the standard deviation of the return divided by the mean of the return. And what this is used to do is to measure a unit of risk per 1 unit of reward. So it's the ratio. Not a very common one to see in practice, but it's a simple formula, so we should remember it regardless. And if we're calculating which the riskiest sector is, it's going to be the one with the highest coefficient of variation. So we can do it really quick. So A, B, C. A is going to be standard deviation of utilities 1.23 over 2.10. B is 1.35 over 1.25. C is 1.52 over 3.01. And if we run these out, bear with me one sec. This is 0.59. This one's going to be like 1.07, just doing mental math. And then this one is roughly 0.5. So the answer is going to be B. An analyst examined a cross-section of annual returns for 252 stocks and calculated the following stats. So we have an average, we have a geometric mean, we have a variance, we have a skewness, and we have an excess kurtosis. Here in this question, we're asked about what is the coefficient of variation. So we just went over this for the formula. So coefficient of variation is the standard deviation over the mean. Key here being the standard deviation. So we don't technically have it in the graph, but we can find it, right? So standard deviation is equal to the square root of the variance. And the variance is right here. So we can take the square root of 0.001723, and we get 0.0415. So this is the S in this equation here. So to solve 0.0415 over the mean, which is the arithmetic average here. We're not using the geometric mean for this formula, it's the arithmetic average. So 0.09986. And our answer is 0.4155, which is close enough to B. So that's our answer. 41, same data set. Now we're just worried about the distribution and whether it's skewed negatively skewed, having no skewness, or positively skewed. So we can see right here, skewness is greater than 0, so it's positively skewed. Um, pretty easy to answer that one if you just know that positively skewed is greater than 0. But to show something really quickly, a positively skewed distribution would look something like this, where you have all the values here on the left-hand side versus a negatively skewed distribution is something like this with everything on the right-hand side. So just got to kind of remember positives on the left, negatives on the right, not really anything else to it, just one of those tricks. For this question, I took a picture off the internet just because I thought I could. This picture draws it a little bit cleaner than I could. I don't want to have any misunderstandings here. Um, but anyway, we're talking about the same chart, and now we have the question compared to the normal distribution. The sample's distribution is best described as having tails of the distribution with less probability than the normal distribution, the same probability, more probability than the normal distribution. So whenever we're worried about tails, we're referring to kurtosis because kurtosis is essentially how steep the distribution is. Um, Whereas skewness, everything's just kind of shifted over here. We're worried about how steep or shallow the distribution is when we're talking about tails. So one thing you just have to know is that the normal distribution has a kurtosis of 3. So this normal distribution right here, and the orange has a distribution or a kurtosis of 3 around its mean. Here in the question, we're actually given excess kurtosis, which you have to be careful about because when we're talking excess kurtosis, we're talking excess over the normal distribution, so over 3. So the kurtosis of this data set is 3.503. So the 0.503 plus the 3. If it was just plain kurtosis, it would be different, and I'll get to that in a second. But excess kurtosis is excess over the mean, so 3.503 in this case. If excess kurtosis is positive, that refers to it's a positive kurtosis, which is synonymous with leptokurtic. So this is when kurtosis is greater than 3. And whenever it's greater than 3, what you're going to have is a steeper shape. So in this blue graph here, we have a steeper shape. And if on the left-hand side, this would be the probability density function. And then here would be a mean, let's just call it like 10. What we're worried about, so we know it's leptokurtic, so it has positive kurtosis, but now we have to figure out, do the tails have more, less, or the same probability as the normal distribution? So if I was to just take a point on the tail, so that's anything outside of the mean, so we can just call it like this point right here, draw a line down, and we'll call this value 9. And if I draw this all the way over here, you can see that this small area here between the normal distribution and the leptokurtic distribution actually there's more probability that the value is less than 9 because this is a bit steeper. The chart would hit the probability up here. I don't know, maybe let's just call it like 30%. That's kind of what it looks like. Whereas over here for the normal distribution, if you drew this down, it's less than this value here. So these tails have more probability of having values less than, or on the flip side, equal to the mean. So in this case, for leptokurtic, it has more probability in the tails and the distribution function than the normal distribution. This was a visual way to show it. Going forward, you just got to know that positive kurtosis is going to be really steep. Negative kurtosis is going to be really narrow. and the steepness of these tails refers to the probability. So the steeper, the more probability in the tails. 44 and 45 we can do together because they're both talking about correlation. So in 44, we have a correlation of 0.34 between two variables x and y, and it is best described as A, changes in x causing changes in y. Not necessarily the case. We could have correlation without causation, so that one's out. B is a positive association between x and y, which is the case because you have a positive correlation. So if I was to draw this out, it's not a perfect linear relationship because a perfect linear relationship is a correlation of +1, which would look something like this, just assuming that's a straight line, where you would have like x and y here. The correlation between x and y, the real one, I'll draw it in green, is probably, something like this, where you have all the values here. It's kind of all over the place, and then it might look something like this. So it's still a positive relationship because it's greater than 0, but it's not a perfect linear relationship. And then C, just in case we wanted to read that one as well, a curvy linear relationship between x and y. Curvy linear would just be something like, it's not straight, it would just be like curved or something. We don't have enough information here to determine that, so it's not C either. 45, which of the following is a potential problem when interpreting a correlation coefficient? Outliers, spurious correlation, or both? So outliers, of course, is just, random extreme values in your data. When you're dealing with any data set, really, that outliers can definitely be a problem unless you're using some measure, which some measures that we discussed later in the curriculum, which account for or adjust the data so we don't have to deal with outliers. So this is definitely a problem. And then B is spurious correlation, which is also a problem, kind of related back to point A here, where we could have correlation without causation. We could have correlation of two variables because they're being impacted by a third variable that we're not considering. So just because something has a strong correlation doesn't necessarily mean that they are causing each other. There could be some other things going behind the scenes that are causing the correlation. So both of these are right, and our answer is C, so both. Next, an analyst is evaluating the tendency of returns on the portfolio of stocks she manages to move along with bond and real estate indexes. She gathered monthly data on returns and the indexes. So what do we have here? We have average and standard deviation of portfolio returns, bond index returns, real estate index returns. So this is, individual measures of distribution. So we have the average and deviation for these two indexes in her portfolio. And then we have covariance of the portfolio and the bond index and the portfolio and the real estate index. And covariance is, very similar to variance, but instead of concerning the variance around a mean of one variable, we're, just analyzing the variance of two different points of two different data sets. So it would be like, x1 minus y1 instead of x1 minus the average of x. Anyway, our question, without calculating the correlation coefficient, the correlation of the portfolio returns and the bond index returns is -0, positive. Okay, so it tells us not to calculate it. The way I like to think of this is we have a formula for correlation, which is actually in the next module. It's a bit weird. But anyway, by exam time, you would know this. It wouldn't be in order of modules. And basically the correlation between two variables is the covariance divided by the standard deviation of both of them. So like standard deviation of x times standard deviation of y, and you're multiplying these two. So if you're just looking at this math equation here, we know that standard deviation can never be negative. It's never going to be negative. So as long as covariance is positive, correlation is going to be positive. And we're doing the correlation of the portfolio returns and the bond index. So portfolio returns and the bond index is positive. So this is going to be 18.9. And doesn't matter what these are because we're just worried about whether it's positive or not. So the answer is going to be positive. 47 is actually the exact same question. We're just worried about now the correlation of portfolio returns and the real estate index. So I just left all my work up here. So we just got to find the covariance between the two, which is negative 55.9. So the covariance, or sorry, the correlation between the portfolio returns and the real estate index returns must be negative. 48, last question in this module, talking about correlation again. So we have two variables A and B. If variable A has a mean of negative 0.56, variable B has a mean of 0.23, and the covariance between the two variables is positive. The correlation between these two variables is negative, 0, positive. So once again, I'm going to bring up the formula for correlation. Correlation is covariance over standard deviation A times standard deviation B. There's nothing related to the mean here. It doesn't matter. Completely irrelevant. They're just trying to throw you off. So we know that the covariance is positive, and this here cannot be negative. So the correlation is going to be positive as well.